One.
Happy Thursday, everybody. This is Dr. Serge, Facebook Live with you all, and I'm planning to do a bit more as we go as well. Today, I wanted to give you an update on this virus because a lot of people have asked me about the way they diagnose people with this virus. And that makes me really mad because the science of it is non-existent, actually. The diagnostic tool that they use doesn't make sense. And I wanted to cover that tonight instead of writing a blog like I do every week. So the way they diagnose someone with this virus is they do a PCR, right? Actually, to be technical, it's an RT-PCR. Okay, so I'm going to use my board tonight. So PCR for polymerase chain reaction. So let's go over a few basics of this test first. Let's talk about DNA. Okay, we know that each single cell has DNA, right? We have 22 chromosomes plus 2 sexual chromosomes, the X and the Y. We have a lot of DNA, so if you stretch all the DNA that we have in one single cell, you will cover about 6-7 feet long. Okay, so we have a lot of DNA. So all that DNA is compacted into our cells using different types of protein. Okay, and we know that the DNA, the cells has machinery to convert or to transform this DNA into RNA transcript. Okay, and from this RNA transcript, the cells will make protein. Okay, so this is the foundation, right? So our DNA, it's about 3 billion base pairs, so it's humongous. So we have a lot of base pairs. Base pairs are letters, right? We have A, T, C, and G, right? So we know that our DNA is double helix, double strands. So we have these series of letters that make our DNA. That's why we call it double helix, right? So we have this double helix going on, right? So these are the letters, these are the base pairs, the nucleotides. When it comes to the PCR, it's a tool that we use in the lab to amplify this DNA, okay? In this case, with this virus, this coronavirus, they do a RT-PCR. Virus is RNA based as opposed to other viruses that are DNA based. So what they do is they use the RNA from the sample, the swab that they do through people's nose, right? I'm sure you've seen the way they do it. So they use a column swab, they insert it to the nose, and they swab the back of the throat, they harvest some cells, and then they go to the lab, purify the cells, and harvest, collect the RNA, and then they add the reverse transcriptase to it, which stands for RT, okay, and to make DNA, because the PCR is DNA based. So they start with samples, viruses, cells from RNA, and then make DNA, and then they can do the PCR. So far, I hope it's so good. So let's go over how this test works. So during my PhD and my fellowship, I've done thousands and thousands of this PCR. So I'm really familiar how it works. And I wanted to go over the basic of this test because a lot of people ask me about how it works and why a lot of doctors now are coming out claiming that that should not be used to diagnose people. As a matter of fact, the guy who invented this technique, Dr. Mullis, actually he won a Nobel Prize because of this. He said that that should never be used as a diagnostic tool. It should be used for research only. Okay, and today that's what they use to diagnose somebody. If you are positive or negative, it's because they use that. So in PCR, what they do, they use a strand of DNA. Okay, and what they do in the lab is they design what we call primers. Primers are small fragments of DNA. Typically, they are within 20, 25 base pairs. And base pairs, like I said, are the letters, the A, the T, the C, and the G. Okay? So what they do is they design primers specifically to amplify a fragment of DNA. Let's say we had this DNA and we want to amplify, make more of this part. So you will design these primers and you will make them, and then you will use them to run your PCR. So what happens during this technique is there's different settings that you need to figure out how to optimize this. Okay? And one of them is what we call annealing temperature. The annealing temperature is to figure out what is the temperature that these primers will bind to this fragment of DNA. And typically these temperature run between 52 and 62 degrees Celsius. Most of the time when I was doing PCR, I would do something in the middle, like 56. So most of the time at 56, these primers that we use would bind to the DNA. And then we add an enzyme that would amplify this part of the DNA. And the PCR is exponential. So you start with 2 fragments, for example, and it gets to 4, to 8, and 16, 34, and so on and so on. So you create a lot of DNA over time. Which brings me to my second point, is the number of cycles. So the first thing we need to figure out is to design good primers that are specific to this part of the DNA. And then the second thing is to figure out the temperature. What is the best optimal temperature to use to do this PCR? And the last setting we need to figure out is the number of cycles. How many cycles we can do to make this part of the DNA. Okay? Most of the time we will not go beyond 40 cycles. And now there's some papers that came up the last few years that say that 40s may be a little bit too much. What happens if you do more than 40 cycles is you start to amplify the background, the noise, and you start having false positive. And the funny thing is the RT-PCR that they run for the coronavirus, they use 45 cycles, which is really at the top part of how many cycles you need to do. My point of that is that 45 cycles is most likely you start amplifying the background, the noise, and you get a lot of false positive. And that's why now people they look into that, and there's a paper that I read that says that about 80% of the positive cases of that actually are false positive, meaning that they are not having the virus at all. But it showed up as being positive on this RT-PCR, so they claim that they have it. So to me, this is totally wrong. This is not science-based at all. So we need to figure out the right setting. Actually, the guy who came up with the coronavirus RT-PCR protocol said that it's wrong to use it to diagnose people. So there's a lot of doctors now that are starting to realize and claim that this is not the way to go. Okay? As a matter of fact, when you use, like I said, they swab the back of your throat and you harvest cells from the throat. But what they don't say is they harvest a bunch of different things. You have bacteria in your throat. You have viruses. You have your own cells. So you harvest a bunch of different types of DNA from different organisms. So when you run this, you have no idea what you actually amplify. And when you start using genomic DNA, which is our genome, so those primers are not that specific. So meaning you may design this primer to amplify a certain sequence of DNA, but you don't know if actually you amplify that specific part. I know from experience when you start using genomic DNA, like I said, which is a long piece of DNA, you never get specific amplification. And it's really hard to figure out the right setting for that. And sometimes I have to say that we try multiple settings to amplify a specific part of our genome, and we couldn't do it because we will amplify all types of sequences that were not specific to what we wanted to do. So my point of that is when they run this test, they have no idea what they amplify. They amplify something, something shows up, it's positive, but they don't know if they amplify the virus DNA or DNA from a bacterial that maybe you had in your throat, maybe because the specificity of the primers were not good enough, they amplify something from your genome. So like I said, at 45 cycle, you start amplifying the background, the noise, and you have no idea at that point what you get, okay? So that was my 2 cents I wanted to talk about tonight, because this is really important. Today, we don't have a tool yet to diagnose people with this virus. I know now they're talking about this antibody protocol test, so which may be better. For that tonight, maybe later, another day. But at the end of the day, there's no way to know who got the virus, who didn't get the virus, because we don't know. We just don't know based on this. Okay? So I hope that makes sense. If you have any questions or something that's not quite clear what I explained tonight, please leave your comments below. I may come back with the blog. So I'm always here to help and address your questions. On this, have a good night. We'll talk to you later.